In a previous video, I've shown you a race condition related to dealing with paths in Linux. I linked the video up there because we built now upon that, so if you haven't seen that, watch that first. And today I show you a similar race condition which appears very difficult to prevent at first, but I show you a really cool trick how it can be prevented, and it's a really clever idea. So here I've created a read flag tool. It's still very similar. It takes a file, it opens it, then uses fstat, like we learned yesterday, to basically prevent race conditions using the file descriptor to get some information about the file. We make sure the file is not owned by root, and then we execute cut. But because we execute a different program, we have to pass to it now the file path again. And already your feelers should start tingling. Ooh, race condition here. Same race condition setup as yesterday. We have an ASD file, which is normal, and a symlink to the root-owned flag file, which we can't read. And then we execute our small racing program. Again, if you don't know this, check out the other video. Read flag 2 is also a setuid binary, so let's attempt to read the flag. It immediately worked. Nice. But you can see if we try it a couple of times, sometimes it will read the empty files, sometimes we get the error that it's owned by root, and sometimes we win the race and we read the flag. So that was pretty clear that this is a race condition. We open the file and check it, but in the end we need to execute cut and have to give cut a file path. And so obviously in the time where we check it, and then in the time where cut is accessing that file, we can switch it out. And this seems like an impossible issue. We can't pass in a file descriptor. So how do we deal with that? Remember my suidbash CTF video write-up? If you haven't seen it yet, you should definitely watch it, but it's not super necessary for this video. I just want to highlight something that is included in this challenge and I didn't mention in the other video. This challenge modified the bash source code a little bit to facilitate the challenge. And basically in there we find the trick that I want to show you. In some way the suidbash setup is very similar to what I showed you right now, but they prevent this race condition. And so this source code includes this trick. So suidbash also opens the file and gets a file descriptor. And then it uses fstat to get some information about that file. And then it has this function can execute to check various things to determine, hey, can I execute that file or not? Up until here, we still don't have a race condition. But the problem is later the original main method is called. The original main method takes a path to a script as a string parameter. And the arguments are prepared here before. But this means, but it's basically the same issue, because here now we need the file path, which then later the normal regular bash program will use to open and execute the script. And so theoretically there could be a race condition where this first can execute check is okay, and then the file gets swapped, and then when the original main is called using that file path script, and then you can execute your malicious script as root. This would obviously be bad. So how did the author prevent this race condition? And the trick can be seen here. So the parameter that are prepared for original main, including the file path, is using fd alias as the file path. And fd alias is created here. It's a path that points to proc self fd and then the file descriptor number. So what is this directory? So the proc file system, we have used it in many videos before. It's a very special file system that gives us a lot of stuff about processes. And in this case, it wants to get information about itself. That's why it uses proc self. But instead of self, you could also use the process ID for whatever process you are interested in. And in there is a directory called fd. So I'm creating here a symlink, a simple symlink just to our read flag program source code. It doesn't matter. So this file is now a symlink. All right. Now over here, I'm using Python. And I'm going open this file now. Next, I need the process ID of the Python process, so we can call getPid. And now we can go to the file descriptor folder of this process. There are 4 folders, 0, 1, 2, and 3. And the first 3 file descriptors, 0, 1, and 2, point to dev pts3. So this is standard in, standard out, and standard error. And then we opened a 4th file, which is tmp hex sym. And that's why we have here now the file descriptor 3. This is the file descriptor that was assigned when we opened that file. And in proc, we have a symlink now to home user read flag 2.c. So this proc file system has this awesome feature that it lists the file descriptors that you are using and has symlinks to the actual file where it's pointing to. So when you now, for example, use head to just print the first few lines of this file, we see the beginning of our read flag 2 program. So we could pass this file to cut, because even if we would do the race condition on this file, cut is not even interested in that one. We use this cool property of the proc file system to now get an actual real safe path to the file that we want to access. So let's simply copy the code from the suidbash patch, and instead of argv1, we now pass the fd alias to it. When you recompile it, make sure you make it set UID again. Now let's execute our racing program again, and now let's try it again. We prevented the race condition. Now let's quickly explore this with the Python example again, because you might think, okay, well, we have here these symlinks to these files, but these are still file paths, right? What would happen if we just switch out that file directly, the readFlag2.c? Let's simulate that. Let's just move it. So here I'm just renaming it from .c to .c.back. And let's look at the file descriptors again. Look at this. Magically, it now points to the other file path. This is the awesomeness of file descriptors. This file descriptor is not just saying, I point to this file path. It's an actual handle to that file. And when you rename or move that file, that handle, that connection to that file still remains. It will always point to that file that you actually opened. Now let's play a bit more with this. Let's do something crazy. What happens if we delete that file? Let's look at the file descriptors. Ooh, now it's red. It says it's deleted. Now, what do you think happens when we read from that file? We still have it open in Python, but it's deleted. So let's read. We got the file content. We were able to read that file, even though it's deleted. This even works over here. Let's use head to read the first few lines of that file. It worked. So even though it points to a deleted file, it still works because the handle still exists. This file is now deleted from the file system, but the handle still exists, so the file still exists. Now imagine you accidentally deleted that file and you want to recover it, and you see that in another program it's still opened. Then here's what you can do. You can simply cut that file and write it back to where the original file was. Let's do that. Now we can read that file. And yeah, it has our content. We recovered the file that we accidentally deleted. Let's have a quick look at the file descriptors. It still says it's deleted. And this makes sense because this original file that was opened was deleted. The file where the handle points to is deleted. Now, there's a file with the same name in the same place, but it's a new file. So it's not the same file, it's a different file. And so this handle still points to the old deleted file. But still, I think this playing around is pretty interesting and cool to kind of get a feeling for what a file descriptor is and what a file path is. I hope you found this interesting, and I personally find this fascinating that this simple line with proc self fd in the suidbash source code carries so much weight that it is there for a purpose. It was there to prevent the race condition, and it has meaning. And you can see this pattern with the proc file system in a lot of applications that basically have to do this. Always when you can't directly work with file descriptors, for example, because you have to pass this file to a different program, then it might make sense to instead open it yourself and then pass the path to your proc's file descriptor.